So welcome everybody to another seminar, Logistics in Quarantine. On behalf of the Brazilian Logic Society and the Logic Interest Group of the Brazilian Computer Society, it's a pleasure to introduce Professor Brandon Fong, who kindly accepted our invitation to give a talk. Brandon, thank you very much.
Thanks, Bruno, and thanks to you and Valeria for the invitation. And I'm grateful to you all are here. It's lovely to speak to new audiences. I think one of the few upsides of the present moment is just the new opportunities to attend so many talks from around the world and to speak to people from around the world. So I'm very grateful you're all here and in the seminar. Today I'd like to present some work that was presented at LIX last year, some work with David Spivak and Remy Thuriès at MIT, entitled Backprop as Functor. So I was encouraged to speak about this. And while it's not quite logical in nature or logic focused, I hope it's adjacent enough to at least to everyone's interest that it'll hold your attention and it'll spark some sort of interesting thoughts and interesting questions, interesting discussion. So I should say everyone should feel free to ask questions at any time. There's plenty of time, and I don't mind going where the audience's attention goes. So to begin with, let me. Oops, sorry, okay. So this talk is really just an exploration of the idea that local learning units can exchange information in a way that leads to predictable global learning behavior. And I don't claim that this is novel or controversial, but I think an exploration, particularly in the setting of supervised learning, is interesting. So it'll be an exploration of supervised learning, so things like neural nets, deep learning, from a compositional, and hence categorical structural point of view. And so supervised learning begins with the interesting observation that there are structures like this idea of recognizing a cat. And while this thing is not necessarily a function, in that it's not completely well defined, you and I might have different versions of it, there's enough of a structure here to model as a function. And a function from sort of space of pictures to a space of judgments about whether the picture represents what we're claiming, a cat. So in this particular model, let's say that a picture is, say, 100 pixels by 100 pixels, and at each pixel value point we have a red, green, and blue value. So a picture becomes a vector in this space, r to the 100 by 100 by 3. And this question, is it a cat, takes a picture and returns a judgment about whether it's a cat. And so it'll be convenient in this particular setting to think of these judgments as forming a vector space, and it's just spanned by its 2 dimensions, spanned by 1 dimension, where the basis vector represents not a cat, and the other dimension, the other basis vector, represents, yes, it is a cat. So, for example, what this function might look like on some pictures, the first picture I have here is a picture of a cat pretty unambiguously. It has 4 legs, it has a tail, and it's engaged in a very cat-like walk. So we send it to the basis vector representing a cat. The second picture is if it is a cat, it's a very abstract representation of a cat. So let's send it to this vector that represents pretty much mostly not a cat. And it's not necessarily the case that this function is really well defined. Different people may have different interpretations, but there's enough agreement that it makes it a useful construct for us to talk about. And it's an interesting problem to think about how we might bring a machine, bring a computer into this agreement about what this function is. So despite this thing not entirely being well defined, not having an easy closed form, how should we program such a function? And what's interesting is that especially over the past few years, for a vast range of things, this problem is pretty much solved. And it's solved for this notion of supervised learning, which involves, instead of trying to program this function in closed form, presenting some structure and then presenting a lot of examples of what the function should do, and eventually arriving at something that functions just as well as we might. So the outline of the talk is to explore this from a categorical point of view. And the first section will just be about exploring the notion of supervised learning from this point of view, presenting sort of a notion of a learner abstractly and talking about how they form a nice compositional structure, a symmetric monoidal category. That'll be largely sort of, in some sense, syntactic, and we want to, but you might want to sort of actually specify learning algorithms or learners. And so this comes through in the second part in sort of talking about, in particular, neural nets as a language for specifying parametrized functions. And then the crux of the talk is in part 3, where I present a theorem which sort of I argue shows that this idea of the backpropagation algorithm used in training neural nets is really about some statement of functoriality. And then in the final section, there's just a question, an observation that similar structures have been showing up recently in other fields and also not so recently. And so the question sort of why that may be so. So to begin talking about supervised learning from a compositional perspective, and to abstract the problem just presented, the goal is to learn a function from examples. So we fix two sets, A and B, a set of pictures and a set of judgments of the truth of a statement, say. And then for all functions A and B, whether it be sort of, is this a cat, is this a car, is this a category, we want to use pairs, sort of A, f of A, so-called training pairs, to eventually approximate this function f. And we want, of course, this method to be independent of the choice of the function f. So the method is to use the following data. We have, to begin with, a set of hypotheses. So I've got a P for parameters. And so given an element P of the set, we get a function from A to B. And this is expressed by this implementation function I. So it's a function from P times A to B, but by currying that, that's just as well a function from P, the parameter set, to functions from A to B. And so this becomes the space of functions we search over when we try to look for a solution to this problem. And the searching is done sort of in two ways. There's firstly the updating of the parameters sort of on the spot. So we have this update function U, which takes a parameter P and then an A-B pair, a training pair, and returns a new parameter P that sort of improves the guess of the function. And then in addition to that, though, we have this additional piece of structure called a request function. And this function R takes, again, a current hypothesis of P and a training pair, AB. But instead of sort of this process of self-reflection saying, I could update my parameter to be more in line with this training pair, it sort of blames whoever gave the training pair. And it says, well, given my hypothesis and the fact that we wanted B as the output of this function, instead of giving me the A you gave me as the input, you should have given me this other A. So I might say, yes, if you really wanted me to say this picture was a cat, you should have made it sharper. It's far too blurry for me to actually make the judgment and sort of present a sharpened version of that picture. So then a learner is this collection of data, this 4-tuple, consisting of a hypothesis set, an implementation function, or update function, and a request function. And we'll view these really, because they learn functions from A to B, as a structure that runs from A to B. So there's a little schematic diagram here where you have an input on the left at A and an output B, but it's indexed by some parameter P in the center. Okay, so that's the learning structure. And the claim that, So to set this up then, what I'm interested in is constructing new learners from all. So we have a bunch of learners and I want to construct some sort of aggregate global learner. And the language I'll present for this is the language of symmetric monoidal categories. So just as a reminder, a category has objects and it has morphisms. So it has objects of A, B, C, and morphisms F from A to B and G from B to C. And what it permits is a notion of composition that says if the output of my function or my morphism is B and input to the next one is B, then I can chain them together, in this case, creating a morphism sort of FG from A to C. So we have this notion of sequential composition captured by the notion of a category, which must be sort of associative and unital to make it appropriately unambiguous. Similarly, sort of a symmetric monoidal category is a category, but it adds this structure, this sort of parallel or monoidal composition. So in addition to composing things in sequence, I can put things in parallel. And so in particular, then, I can talk about sort of given an object A and an object B, I can talk about an object A tends to B or A times B, which puts them together, and similarly for the morphisms. And these are, of course, subject to the parallel composition is also subject to some associativity and unitality constraints, as well as some sort of nice coherence or compatibility constraints between the sequential and the parallel composition to make them well behaved. But the upshot of this all is that it provides an unambiguous interpretation of string diagrams like the one on the slide here. So in particular, you see sort of sequential composition between these sort of boxes, these morphisms F, G, K, H, but also that they're placed in parallel. And crucially, in the symmetric part of the definition, the symmetric monoidal category, we can sort of braid wires, so we can swap wires around with really no consequence. They sort of pass through each other. But then a symmetric monoidal category provides a way to unambiguously interpret this sort of diagram, this sort of syntax. And along with the notion of a monoidal category, you get a notion of a monoidal functor. So just as a functor is an appropriate sort of structure preserving mapping between categories, you can ask that the monoidal with the parallel structure be preserved too. Okay, so the claim then is that these learners form a symmetric monoidal category. And to get the category part out of the way, the objects are the sets, these sort of sets of pictures or judgments about whether it's a cat or not. And the morphisms are these learners that I presented on the slide before. So we've talked about learners as running between sets A and B. More properly, just to take care of size issues, I should talk about the morphisms as being equivalence classes of learners, but it really is no sort of material consequence to the key ideas. But of course, that category has composition, and so the question here now is, how do we compose learners? So say we have a pair of learners, one sort of written PIUR, which learns functions from A to B, and a second which is written QJVS and learns functions from B to C. I want to be able to produce a method in this framework for learning functions from A to C. So in particular, I first need a parameter space, and the parameter space is just the product of the two parameters, spaces of the constituent parts. Because if I have some value P that sort of specifies a function from A to B and a value Q that specifies a function from B to C, then I get a function from A to C by composing those two functions. So this parameter space Q times P accurately indexes morphisms from A to C. So to sort of tell you precisely what the implementation function is, I'll introduce string diagrams. It'll be slightly easier to read, but string diagrams in the category of sets with the monoidal structure being given by the Cartesian or categorical product. And here, the string diagrams are sort of quite nice to read. So for example, this implementation function I represents the function from P times A to B. And it's depicted in this way, where I have sort of two pipes coming on the left, one carrying a value of P and the other carrying a value of A. and then it spits out sort of on the right a value of B through that single output channel. And to depict the update and request functions, it's easier to pair them as you can, because the product here is the Cartesian or categorical product. So I draw this box U comma R to represent this function that takes in sort of a P and A and B, a parameter and a training pair, and returns this new parameter and this new input value. Okay, so then here we can write down the composite implementation function. It's exactly sort of this intuition I just described, but so more explicitly, it's written either in the usual sort of algebraic function notation below, or in string diagrams above, and it says that you take in this value A, you have these sort of parameters P and Q that determine some functions according to I and J, and you sort of compose in the way described. To get the new update and request function is a bit more complicated. So above it's in string diagram, and below it's in again this usual function notation. But while I won't sort of make you try and read all of that, I can describe the intuition. And the key intuition is that composition is about creating local training data. Because I have, again, I begin with this sort of parameter, PQ, and this gives me a function from sort of A to C when I compose I and J at those parameters. And I'm also giving this AC training pair. But to update, I need to update the Q P and update the Q. And the method I have given from the parts is just this, just these update functions U and V that update these parameters locally. So I need to use that structure, local training data. So I need to produce an AB pair to update using U and a BC pair to update using V. To get a B is sort of very straightforward here. We have this parameter P, and we have this input A, and we can just evaluate I at P and A to get a value of B. And this is appropriate to constructing a BC training pair for the second part. But that we need that value of B is not appropriate for training the first part of the function, because, well, it's the value already output by the parameter, the hypothesis at that point. So if we just fed sort of that value back, there would be nothing to learn. And so this is where this structure of the request function comes in. And so luckily we had this extra way to produce another value of B, and we produce it by applying the request function at this new B value, IPA, as well as Q, the parameter Q, the hypothesis for the second part, and the output value C. So this produces this other value B, written in the center of the slide here, S of Q, comma, I of P, comma, A, comma, C. And so now we have an AB training pair and a BC training pair, and we can apply sort of our functions U and V to update them to new parameters P prime and Q prime. And the request function is similar. We sort of pass the request value back as we see there in sort of the third line. And then we use the request function R from the first morphism to pass that back to a new value of A. So I claim this as a symmetric monoidal category. The monoidal structure is just sort of is just to do things in parallel. So if I have a method for learning functions from A to B and a method for learning functors from C to D, then I can just run them in parallel to get a method for learning functions from A times C to B times D. And the upshot is that perhaps despite a sort of slightly convoluted method of composition, this data does form a symmetric monoidal category. So it is sort of associative and unital in the correct way. And so then I claim this provides a compositional framework for supervised learning. Learning because it's about updating parameters, updating these hypotheses. Supervised because the learning is done according to this training by input-output pairs, so by providing these lessons, so to speak. And compositional because we have this categorical structure that allows us to talk about building new learners from old. Okay. Are there any questions at this point? Okay, I'll move on. Sorry?
I have a doubt, a silly doubt. Was that category named symmetrically?
Why is the category symmetric? You can construct, so to get the symmetric structure, you need a braiding. So I need a morphism from A times B to B times A for any AB, right? And so you can always construct, going back to the definition of a learner, you can sort of embed the world of functions inside this category, because you can just choose the hypothesis set to only have one value, right? So if you eliminate that, then it just ends up being a function from A to B, as well as, I guess, a function from A times B to A. But so if you choose the request function to be a projection, and then you're free to sort of choose the implementation function to be whatever you want. And so the category of sets just has this braiding, so this usual map that executes the symmetry from A times B to B times A, which just takes the pair AB and returns the pair BA. And so you can use that structure again in this category, and it obeys the necessary laws.
Okay,
Valeria?
thank you very much.
Yes, thank you. I mean, I'm glad you are back into this particular slide, because my question is about the amount of information that's buried on this set in the set P. You know, I can keep in my head that A is a collection of pictures, and I can keep in my head that B is just a label for it, and these are kind of fairly atomic sets in somehow. But the parameters, you know, they are the mysterious things in machine learning. So, I mean, I wonder if you can say something to help to help us kind of make me feel less worried about the fact that, you know, the way I was thinking about parameters before, they would be things like if there's a curve for a tail, then or something, or if it's, you know, there's so many things that could be a parameter, and we just kind of putting them back into a set that we are not going inside, look, call it P and be it.
That's a really good point. This abstraction is perhaps too abstract, and it's leaving out key features. And so I'm perhaps you'll be somewhat sort of more comfortable in the next section when I want to add a bit more structure to these sets, and in particular the parameter set. I agree that in any sort of practical machine learning case, we actually need much more structure to describe what's going on, to actually execute, for example, gradient descent. So that'll be evident in the next sort of half hour. But if it's still not enough structure, then I think we should discuss again at the end.
That's great. Thank you so much. I mean, that's good. That's really good.
Okay. Great. So again, back to the question: how can we explicitly construct a learner then? Because again, as Valeria has just pointed out, this is all far too abstract, and it's not really clear that this structure is capturing enough of the problem to be interesting. So my claim in this section is that neural nets are a way of specifying parameterized functions. So no more, no less. And well, the other feature that they have going for them is that they're nice and combinatorial, so they're very easy language to use for this purpose. So to discuss what it means to specify and construct parameterized functions, I want to introduce a new symmetric monoidal category of parameterized functions. And this is where I'll sort of start putting in a bit of extra structure. So here, the morphisms, the objects are going to be finite dimensional vector spaces, which is maybe too much structure, but it's convenient to make the point. So we have these objects, finite dimensional vector spaces, and then these morphisms are just the first two parts of the data of a learner. So a morphism from Rm to Rn is a parameter space, in this case, indexed by a natural number, so here R to the k, and then a differentiable function, so again called I, from the parameter space R to the k times the input or domain R to the m to the codomain R to the n. And then composition is, as for sort of composition of implementation functions in the previous category learn. So if I have one of these functions I and another differentiable function, this time from R to the L times R to the N to R to the T, called J, then I can compose them in the way depicted here. So that's also a symmetric monoidal category. And now neural nets, I claim, are a way of specifying morphisms in this category. So to make this more precise, the sort of catchphrase here is that a neural network is a sequence of bipartite graphs, and these are a compositional combinatorial language for specifying differentiable parametrized functions. So here is a neural net. It's a very simple one. It's a sequence of two bipartite graphs, so it has depth 2 in the language of deep learning. And the first graph is a bipartite graph, a sort of a 2-2 bipartite graph with 3 edges, and that's the second is the complete sort of bipartite graph on some 2, 1 vertices. So how does this specify a differentiable parametrized function? So the intuition is biologically inspired, and I'll just sort of talk about the first layer first. So each node represents, in this sort of biological analogy, a neuron, and these links represent sort of the signal flow from left to right. So here, in the second layer, the top neuron 1 receives a signal from both the neurons on the previous layer. And these neurons the signals are weighted by sort of a strength of connection, and then sort of and then modified by some sort of threshold called this bias. So then, how this layer here represents a parametrized function. First, what is the domain and the codomain? The domain is equal, or has dimension equal to the number of input or number of nodes on the left of the layer. And the codomain has dimension equal to the number of nodes on the right. So this is a parametrized function from R squared to R squared. Then we get to the parameters. And so the parameters are a weight for each edge. So there are 3 edges, so there are 3 weights, and a bias for each output node, which again is this sort of idea of an activation or a threshold. And so therefore, this graph has 3 edges and 2 output nodes. So it has 5 parameters. And then to extract this differentiable parametrized function, I have this function sigma, which needs to be specified, but it's a differentiable function that is of your choosing, called the activation. And again, so traditionally you use sort of step functions to indicate this idea of some sort of binary threshold. Does the next neuron get activated or not? But obviously that's not differentiable. So you in machine learning applications, you use various sort of things with nice derivatives that approximate that idea to some degree, even though that degree might be very loose. In any case, this means that the function you get here, it takes as input some vector p of these 5 parameters and some input vector a, sort of has components a1 and a2, and we get out sort of two real numbers. The first is given by sort of the linear sum of the a1s according to the first parameters associated with the edges coming in, so p11 and p12, and then we add the bias at the end, and then we put it through the activation function. And similarly, to get the second value, there's only 1 edge, so it's just the first value A1 weighted by this value associated edge P21, and then we add the bias associated to that node and put it through the activation function sigma. So then to get the function associated to a network with multiple layers, we just compose these functions. So now here in this 2-layer network, we have, it represents a differentiable parametrized function from R2 to R, because there's only one node on the final output layer now. And it's given this by expression. So essentially a linear sum of the previous 2 output values that we saw, plus the bias, and then put through again the activation function. Okay, so I claim that there's a category of neural nets. It's sort of a free category on sort of bipartite graphs. So the objects are natural numbers. The morphisms are these neural networks, these sequences of bipartite graphs. And to compose, we just concatenate. So this is a way of sort of a combinatorial way of describing these bipartite graphs, these neural networks. But then this is not a very insightful theorem, but it says that given a neural network, once we specify an activation function sigma, we get a differentially parametrized function in the way described on the previous slides. So one thing I want to note here is that while this provides a convenient syntax for talking about differentially parametrized functions, what's really important is to get these functions at the end. And we'll see that in the next section when we talk about backprop, really as a way to extract learners from parametrized functions. And talking about these things in this way gives us an opportunity to reflect on sort of different languages that we might use to construct parametrized functions. So another language which is slightly more general, so strictly more general, but only slightly, than the one just described, is to begin with some set of primitives in the category of parametrized functions, and in particular these 5 primitives, and then to use the syntax of monoidal categories to talk about composing and constructing new terms. So I've done things diagrammatically, but they can be done algebraically as well. The 5 functions I want to pick out as sort of interesting primitives for constructing parametrized functions effectively capture elements of what I was just talking about and how we interpret neural networks, these bipartite graphs, as parametrized functions. So in particular, there's this morphism which adds 2 vectors, a morphism that sort of takes in a value and duplicates it. And again, these are parametrized functions, but they're unparametrized in the way that was that question by Petruccio described earlier. So you can sort of see these functions here and just think of them as having a trivial parameter space. Sorry, that's actually irrelevant. We don't need a learner. We don't need a request function. It's just if you make it the parameter space trivial, then a parameterized function is just a function. So here we have the first 3 are just functions. Addition, duplication, and this activation function. And the last 2 just have a one-dimensional parameter space. The first one has a parameter space but no input, and that's a bias. It just sort of spits out constantly whatever a parameter it's at as a bias. And the second is a weighting function. So it stores a weight W and takes as input a value X and returns X weighted by W. Okay. So we have some primitives. And so to construct the notion of a neuron with these primitives, we can sort of write down this function here. So here we see we have some inputs. We weight them by these parameter spaces. We add them together along with the bias, and then we put everything through the activation function, and then we feed it through to any downstream neurons. Okay, so the reason I mentioned this is that often in applications of machine learning, you have this neural net, but you want to add some sort of structure external to the actual syntax of neural nets to control your learning. So a simple example comes from machine vision, where sort of you might have a series of, so you're trying to interpret, say, the image on a screen. You have a series of neurons dedicated to receiving input from, say, the top left corner, and another to receiving input sort of adjacent to that. So in a similar sized area, but maybe slightly to the right of the top left corner. And a lot of structure in vision is just locals, for example, corner or edge detection. And so if these parts of the brain, if these parts of your network are looking at two different things but performing the same task, they should have the same sort of connection structure, the same weights and biases associating these different actual sort of neurons. And so to enforce that, it's useful to talk about a technique called weight tying, which basically says these are edges connecting different sort of neurons, but they're performing the same sort of task. So we want to enforce them to have the same weight, the same connectivity pattern. And so this can be expressed natively in sort of this language of parametrized the sort of language generated by these primitives inside the category, the symmetric monoidal category of parametrized functions. And the key idea here is that you can externalize weights and share them. So in the first line here, we see an equality between a parametrized function and a composite of two parametrized functions, one which just sort of captures the weight and, the parameter and outputs that value, and the second which is about the implementation function. And so to tie two weights together in the syntax, or to present a category where, a structure, parameterized function where one weight informs multiple parts of the network, so to speak, you can use the copying structure to feed a single externalized weight into two different functions. And so you can express weight tying natively in this syntax. So it's interesting, I think, to if you're thinking about specifying machine learning algorithms, you can sort of play with these ideas a bit and see if you can find interesting ways to express more general frameworks. Up to the fact that, of course, the syntax of symmetric monoidal categories, even some sort of reduced fragment of that, is more complicated than simply talking about bipartite graphs. And so that's a cost to bear. Anyway, any questions on that part? Okay, I'll move on to the main point, and there'll be plenty of time to talk at the end too. So the main point is that from these parameterized functions, you can construct sort of these learners in an abstract way that I discussed. And the way you do this is via gradient descent. So here's a simplified version of the main result. And it says that for any epsilon greater than 0, so you think of this as a step size or learning rate, there's a strong symmetric monoidal functor from parameterized functions to learners, which takes a parameterized function and constructs an update function and a request function for it, essentially according to gradient descent. And so here, there's an implicit notion of error, but how we update, say, the kth component of the parameter, sort of p sub k, is that we take an epsilon step in this direction dictated by both the difference between sort of the ideal jth component, bj, specified by the training data, and the hypothesized jth component specified by the parameter, so I sub j of pa. And that's weighted according to the influence that this sort of jth component, the influence that the kth parameter has, component of the parameter has on the jth component of the implementation function. So we sort of do that weighted sum, and then we move an epsilon step size in that direction. And the request function is similar in spirit, although it's sort of it's more blatant. It doesn't take into account the epsilon. So that's the specific case of quadratic error in some sense. So if you look at the bottom right-hand side corner of the slide, there's this notion of quadratic error, which basically says that the sort of cost we associate to a difference of x and y is proportional to the square. So difference between hypothesized value and actual training value. More generally, we can sort of look at the properties that we need to make this happen. And so we have this theorem that says we fix both a step size epsilon and then a cost function, sort of r times r to r, which takes in two values, so two components, the actual and the hypothesis, and returns a number describing how well or how badly we did. And this has some sort of technical differentiability and invertibility condition. But once we have a step size and a cost function, then we can construct a nice functor, in fact, sort of faithful injective on object, strong symmetric monoidal, from the category of parametrized functions to the category of learners that does the same thing. It takes the parametrized function and constructs update functions and request functions for it according to basically gradient descent, taking an epsilon step size and the derivative of the error, and similarly requesting something described by the error. Okay, so what's happened here? What is the point of so this exploration and then this theorem? Firstly, I think it's good to lay out the structure of the problem of these techniques of machine learning within this sort of categorical framework. So you can kind of see where different aspects of the problem lie instead of having it all in sort of one big soup. And so you see this sort of category of neural nets, again, as I just argue, as a combinatorial way of specifying functions. So once we specify an activation function, we can turn these neural nets into parametrized functions. And there we can talk about things like weights and biases, like tying weights together, and how this leads to structures in sort of machine vision, like convolutional neural nets. And then if we specify, in addition, a learning rate and steps or step size and a cost function, then the gradient descent gives us a method for turning these parametrized functions into sort of these learning structures, where then we can talk about updating parameters and training data. And in particular, we can talk about a backpropagation. So the idea here, and this is not meant to be a subtle point, but just something that this exploration, I hope, has brought out, is that the gradient descent can be computed via message passing between sort of the substructures of a network. And this is really a statement of functoriality. So here's an example of a neural net that I pulled from this website. And it's still, in fact, compared to industrial applications, a toy example. It's common for industry neural networks to have sort of millions of nodes in a layer and have more layers than this. But you can see, looking at that structure, this is at each node, we sort of shove things through an activation function, and we get this highly nonlinear structure, which is function, which is possibly incredibly hard to differentiate. It has, at the very least, very many parameters. And what enables us to work through sort of problems of gradient descent on sort of these large, highly nonlinear functions is the fact that gradient descent can be computed locally in this functorial way. So we know that we can view this as the composite of, if we like, down to individual neurons or substructures below little individual neurons. And passing this sort of factorized version through the functor means we get this network of learners that sort of update locally and then pass around requests and hypotheses. And this is much more computationally efficient than trying to do the entire composition in this sort of parameterized function category and then shoving that through the functor and hoping to differentiate the composite thing. So again, to the slogan I put up on the first slide, the idea here to think about or to meditate upon is this idea that local learning units can exchange information in a way that leads to predictable global learning behavior. And so this is a particular example of that case. How are we doing now? Any questions?
Yeah, question again.
Okay, great.
Can we go back to the first slide again? Because I mean, I think I do not get completely what the requester and I think.
Just the very first slide.
Yeah.
Mm-hmm.
Sorry, I'm very slow. So we have this update and the request and the implementation, right?
Mm-hmm.
We're going to have the error, which is the thing that most people associate with learning. That's going to come in, and now I want to go and see the slide that has all the categories in parallel, one after the other, please.
Okay.
Yeah, more.
This.
No, more than that. One more.
No.
Yes, this one. So we made part of the neural architecture the notions of update, and I mean, I'm kind of baffled a bit by the fact that the cost and the error are at the end and not at the beginning. In that, it's more important to tie the weight. So
Yeah.
It's not sets, it's vector spaces. That's fine. That's was expected, right? Because that's what everyone else does. I mean, if you're doing machine learning, you're doing vector spaces. But so the weight tying is okay where it is, but the fact that the error and the approximation come later, that kind of worries me a little bit, because we know we're missing a theorem, right? We're missing a theorem that says that the gradient descent that we have here is the gradient descent that we have in in the applied sense. Or aren't we? I mean, maybe
I don't,
because I didn't see it, but
so to me, when I don't know what you mean by the gradient descent in applied thing. So we have so I claim that gradient descent here is exactly the same as gradient descent as it's put into practice. It's sort of moving. You have your error as described by this update function line. You have this error and you sort of compute that, and then you move a small amount in that direction. And there's the interesting result of the functoriality says that when you assemble your sort of local learners doing local gradient descent, it corresponds to doing global gradient descent because of the functoriality, because that's the same learner results, whether you work locally first or you work globally first.
I see. Oh, that's very helpful. That's
okay.
Helpful because, so it is about doing computations locally that you actually know work globally as well.
Right.
Knowledge is giving you that.
Mm-hmm. Yeah, that's I think the exciting part of this for me. It provides a very clear statement of how that's happening. I do take your point about it's slightly confusing. Well, I can imagine that there are other ways to divide up this picture that really associate the cost or the error much more in the notion of learning, because it is a bit strange that, for example, in this category of learners, there is no guarantee that it's actually converging. If you feed it coherent data, that it's converging to some nice understanding of what's going on. You could just have your update function be, I refuse to change my parameter, and that maybe doesn't deserve to be sort of called some learner or some notion of learning. And so it'd be nice to have some results that at least say that, I don't know, for maybe if we carve out some subcategory of learners that have nice properties, then when we compose them, nice properties are maintained, and these nice properties state that, you know, if you feed it coherent data, then it like always gets closer to the true function or something like that. But those guarantees are actually quite, they often violate, I haven't found examples that don't actually violate practice, in that machine learning is not that clean. You can feed something good data, and through some sort of mysterious fluke of the choice of error function or something, or just you can take a step and you can get further away from the truth or something like that. And that seems to me an important feature of what's going on, actually. So I haven't found a way to sort of capture that in this picture.
Thank you very much. That is very helpful. But yeah, I think, you know, mathematicians that I know that think about optimization in general, you know, they think that their main job in life is to prove the approximations are working, right? So, you know, that's the main idea, is this business that we go for things that we can prove are getting better. And that's yeah, kind of, I mean, it's good. Category theory sometimes goes in its generalized ways, right? And then you see a different picture. So yeah, no, that is very, very exciting. Thank you so much.
Yeah. I'll say a tiny bit more, which is more to just pose a mystery. And that's an observation of that this structure is reminiscent of other structures. I'll just mention two recent ones, the learners and open games, just because I have some nice theorems about them. But it sort of goes back to, for example, your work, Valerio, on dialectic categories, or indeed then to maybe Gödel's work on the dialectic interpretation of intuitionistic logic. But there's a structure, the interesting structure here, I think, is that we're expressing something about bidirectional information flow. And in fact, that might be more true than this idea that we're expressing something about learning itself. And so, for example, you have this notion of lens or bidirectional transformation coming from originally database sort of view update problems in database theory. So the central problem, for example, is that I have my computer here and some sort of shadow on my computer or some larger database in the cloud. And I want to be able to talk about sort of retrieving the state. So A here in this asymmetric lens is the state of the cloud, and B is my computer. And I want some way of sort of projecting that state down to my computer. But also, if I modify my local state of the computer, I want to be able to push that back up to the cloud. But obviously, the whole state isn't contained, so I need this sort of get function, which is interestingly named. I won't talk about the intuition behind the name because that escapes me at the moment. But it takes a state of a global state from the cloud and a local state from my computer, and sort of pushes that up and creates a new sort of global state in the cloud. And we can see that this is, in the way that we were talking about before, obtainable just as talking about learners that don't do any learning, that they have a trivial hypothesis space. So if we make P a one-point set, then exactly the hypothesis set is irrelevant. The implementation function is just a function from A to B. Update function is, again, trivial, and a request function is a function from A times B to A. So it's just a straight up observation that you could sort of embed asymmetric lenses into learners in this way. But it turns out that more interesting than discussing these asymmetric lenses is discussing symmetric lenses, which are just sort of two asymmetric lenses pointed in opposite directions. And the idea here is that A might be my computer, B might be your computer, and X is the cloud. And we want to sort of maintain some sort of coherent state between my computer and your computer. And so we have this sort of span of asymmetric lenses. And so there is a way talking about these things called constant complement lenses, which is sort of this projection, which exactly has this projection intuition. But we see on the bottom left a map from P times A to A. That's just sort of a constant complementary projection type lens. And we see that you can embed in the other direction learners into symmetric lenses rather than lenses into learners through exploiting this structure. So that's sort of an example of a connection between learners and lenses. And another framework that has been discussed recently is open games. And the observation here, or the research program here, is essentially to take the idea of a microeconomic game, which say captures, I don't know, a prisoner's dilemma, and note that economic interactions are more than just isolated prisoner's dilemmas or isolated games, but you want a way of talking about chaining them together, both sort of in time and in parallel. Right, and talk about some sort of aggregate game, which gives you a better notion of economics. So I won't go into any detail here, but again, the solution is to talk about this notion of open games, which has, again, this flavor of bidirectional implementation, bidirectional information flow. You sort of feed forward sort of strategies and actions, and what comes back is sort of co-utility, so the sort of results of your actions. And again, you can sort of formally relate these two structures of learners and open games, and there's been further work really exploring this connection. But then I guess just sort of a mystery to me, and maybe a question that is interesting to approach from a logical point of view, especially with the connections with dialectic categories and the dialectic interpretation, is just sort of what is going on here? What is this logic of bidirectional information flow? Is this a coincidence, or is there some structure here to really explore? So just to summarize, there were 4 parts. I talked about sort of this category, symmetric monodal category of learners. I talked about this symmetric monodal category of parametrized functions and how neural nets embed into them. And I talked about how to move from a parametrized function to a learner via this backprop functor, which again sort of captures this notion of, I think, backpropagation and why it's sort of why it computes the right result. And you can sort of also see then that you might get efficiency gains by using some sort of factored system of learners rather than some sort of totalizing global learner. And then finally, sort of an observation that there is some notion of a logic of bidirectional information flow, and there are hints that it's showing up elsewhere, but that's more a mystery to explore than any real sort of claim. So a couple of references, but mostly I'd like to end by just saying thanks and open to discussion.
Well, thank you very much.
Thank you very much, Brandon. Yeah. So now we have some time for questions, comments. Valeria would like to make some comments.
I always want to ask questions, but I was going to let everyone else have a go first, you know, if they, I mean, but while they are thinking about their questions, Brandon, please put back the slide of the symmetric lenses. Just a sec while people are. So we don't have update anymore. We have get and put, and they are.
Oops, I'm missing a B on the update. Yes, so we have 2 asymmetric lenses, and one of the asymmetric lenses is trivial in the sense that it just projects out a complement. So that's the left leg of the span, And the right span is an asymmetric lens from P times A to B. And if you explore what that structure says, then it's a get function. So it's a function from P times A to B, which is an implementation, which can be seen as the implementation function. And then this sort of put function, which goes from P times A times B to P times A, which is exactly the data of an update and request function.
Okay, I think I see it. Yeah. I mean, I need to think about that one. Thank you.
Yeah, it's odd. It's difficult to know what to make of this, but it's sort of very on the nose. So it's tempting to wonder if there's some significance in it.
Yeah. And you did that with
Mike Johnson.
And do you know what he was looking for?
I don't want to speak to his motivation. He gave a nice talk on this sort of thing at ACT 2019. I think it's recorded online, but
okay.
Yeah, no, I can't really answer exactly what his motivations were. It is tempting to think about sort of learning in the context of, so lenses, as you know, sort of have moved from this sort of database problem to a general structure for control flow. And it is tempting to try and merge that with some notion of learning. And I think he's thought a bit about that, but I'm not sure that anything's been written.
Right. I still don't see why it's symmetric. I mean, there's still a map from A to B. So where is the symmetry coming up there?
Oh, it's symmetric in that it's a span, and it's invertible in that sense, or it's sort of reflectable in that sense. So I would say this is the dagger like the category of symmetric lenses is a dagger category.
Right. Okay.
So that's a notion of symmetry.
Thank you.
But you're right, it still runs from A to B, and that's important. I guess what makes this a sort of genuine result is that it's not obvious that the composition should agree, because composition of asymmetric lenses is symmetric lenses is via some notion of pullback, but the category of asymmetric lenses doesn't actually have pullbacks. So you've got to sort of fudge things a bit. But somehow the natural notion, you follow your nose, and there is a somewhat natural notion, and that notion corresponds to the notion of learners, of composition learners.
Yeah, no, I don't think I followed that one quite yet.
Yeah.
It's interesting.
No, that's not obvious.
Yeah. Thank you. Now I'm going to shut up and let someone else ask questions.
Yeah, thanks for the questions.
Any other question or comments?
Well, if I may complement one comment now, I had all my questions, but I want to make one comment, which is about how this relates to logic, right? And it is kind of because the lenses and the dialectic and stuff like that are models of linear logic, and it is interesting to see if in general. And of course, I mean, of course, I don't know how, of course, but vector spaces are the traditional model of linear logic that actually gave it its name. It's about linear algebra, so kind of it's about adding vectors and multiplying by scalars and stuff like that. So it has a very good feeling of coming home to roost, right? And that's why I thought it would be very good for people to see in the logic seminar kind of a very, and we had already one seminar on machine learning and logic, and that's a different version of that. So thanks very much for coming and talking, Brendan. That was lovely. Thank you.
Yeah, thanks for the invitation again. And I really, do hope to see this subject explored. So if you have ideas, please let me know.
I have a small question, Petruccio, here. Maybe is this connected to the category of relations that people call allegories?
Yeah.
Or not? So it will have a direct connection to logic.
The symmetric version should be related to allegories, because allegories are the way that people model categorically this sort of symmetric relations of sorts. But I don't know for a fact, it's just a feeling one has that there is this.
Yeah, I don't know how to make that formal either, but I would make the same response. So somehow symmetric lenses are like the allegory spot corresponding to the category of asymmetric lenses. I suspect you can't do all the, it's not sort of quite rich enough to support all the logical structure, that like the regular logical structure that you can do in an allegory, but there's some analogy to be made.
Yeah.
And I guess learners fit into that picture then, since they embed into this category of symmetric lenses.
Okay, thank you.
Any other question or comment? Well, so thank you very much again, Brandon, for accepting our invitation. It was a really nice talk.
Thanks for being a great audience. It was lots of fun.
Thank you, Brandon.